Welcome to RCast, the official podcast to the RChain Cooperative. RChain is a complete, concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. I'm Derek Barris, the Director of Content for RChain. Each week on RCast, I'll be talking with the founders of our portfolio companies, as well as co-op members, staff, and other figures in the RChain ecosystem about the most pressing issues in blockchain today. Please check out rchain.coop to learn more about the platform, our community, validator sale, and information on becoming a member.
In the last, not the very last RCast, but the one before, we spoke about error correcting codes and kind of gave a surprise twist ending as to how it related to perhaps some larger issues. I actually hope this will be sort of a two-part series. So I want to talk a little bit about using biological metaphors to think about the sort of distributed consensus platforms that we've been talking about with the proof of stake and Casper. Obviously, since the previous work was all about getting liveness constraints, fitting those two together, but then sort of opening up to that wider perspective, the larger perspective, to see that these two lines of research actually fit together in another way. And that other way is an attempt to begin to develop a notion of a living world. A lot of times, the sort of canon of Western science, life doesn't exist at the ground. Life emerges as a phenomenon above that. I want to propose an alternative, a view in which life really is available sort of at the ground, from the ground level up. We don't have to jettison or discard what we've come to expect out of scientific rigor and scientific precision and formalism, mathematical formalism, in order to address a more living world. So that's kind of the larger perspective. Let me dive into some of these biological metaphors to sort of help get things rocking and rolling. Part two of the overall talk is lifelike agency and consensus. Recently, my attention was attracted to an article in which a group, I think it was at Indiana, but I can't remember exactly where they were based, had built some lifelike materials. So the material was self-assembling, it was self-replicating and metabolically controlled. Pretty lifelike under many respects. The question came up for me, can we formalize this notion of lifelike behavior? And that is the starting point for this piece of the work that I'm trying to lay out here. The first question is mere resource constraint lifelike? On the slide that I have in front of me, and others can see when the podcast is up, if we write down some row calculus processes where we have a process that is, hunting for food from some food source, right? So for food from S, where S is the source, do P. So if we just make P be that minimal thing, which is to hunt for food and then continue. If you put that in parallel with an environment that supplies some finite amount of food, so that would be P of S in parallel with E of S, where S is the channel along which the food gets transmitted. If E is really just the parallel composition of a bunch of food-generating events, you're sending food on S in parallel, maybe N times. Then after N transition steps, that parallel composition just goes back to being P of S. Does that make sense, Christian?
Yeah, you're just eating all the food.
Exactly, eating all the food. But the interesting point is that P is not very lifelike, because if you put it back into an environment that supplies more food, P just continues. It's hardier than a tardigrade. Can't ever die. And that sort of, in my opinion, helps us understand what is lifelike. Lifelike processes need to be able to die. A thought would be to do something that's kind of two-level. So on the outer surface of this lifelike process, it's searching for food, but on the inner behavior, in some sense, the continuation of having received the food, we convert that food into energy. we might want to look at, the conditions under which or how that energy is deployed. You can kind of check and see, well, if we've got enough food, then we'll convert it to energy and make it available through some metabolic channel. And if there isn't enough food, and again, this is just a cartoon, we're just sort of characterizing the rough shape of life. If there isn't enough food, then we'll trigger some kind of shutdown process. In the case of cell dynamics, that would be called apoptosis, which kills the process. We can make that decision independent of the continuation of the process, right? So there's a decision-making apparatus, and that's running in parallel with a selection or a choice, where the choice is either we get energy from the metabolism, or we get the signal to trigger apoptosis and we stop. Separating the decision from the continuation behavior is kind of important because it makes it modular, right? And then we might compare that to another behavior where we're searching for food and we just check to see, is this enough food, in which case we continue. And if it's not enough food, then we stop. That's sort of a one-level process rather than a two-level process it doesn't really have any real internal logic other than checking to see if that's enough food. There's no autonomy inside the continuation. It doesn't have two parts to it that are effectively independent but interacting.
Yeah, I can't decide between different actions to how to use the energy.
That's correct. That's exactly right. If we think about it, one of the interesting things is that metabolically controlled continuation, where continuation means sort of the continuation of the lifelike behavior, it's not the only discernible feature of life. Life also autonomously reproduces. You could imagine leaving the decision part alone. So the decision is checking to see if we have enough food to continue or where we need to shut down. But changing the continuation behavior so that it's more refined. You leave in the options to just continue at per status quo or to shut down, but you add in another option. Now let's imagine that we have two channels, right? So we have a metabolic channel and we have a reproduction channel, and then we do a join on both of those. So we're going to get some energy off the metabolism, and we're going to get some other energy off of the reproduction channel. And then we'll sum the two energies together. And if it turns out that we have enough energy, whatever enough means, from this sum, then instead of just continuing, we will duplicate this lifelike process. It'll do more than just continue. It will be like a cell undergoing mitosis. It'll split into two.
Do you mean that you are receiving energy from the act of reproduction, like you're not thinking of necessarily one individual, but a small group, and reproducing is increasing the total energy, or you're receiving energy that's devoted specifically to reproduction?
Receiving energy devoted specifically to reproduction. So we imagine that the metabolic channel and the reproduction channel are effectively internal channels. The check that we do when we sum the two energies, one from the metabolic channel, one from the reproduction channel, either it's enough, in which case we go ahead and reproduce with the cell divides, or we take the energy that we've got, which is the sum of the energy that came from the food and the energy that came from the reproduction channel, and we put it back out on the reproduction channel. So we've squirreled away some of the food energy for reproduction. And this is very similar to what we see in reproduction in life. The organism that's capable of reproduction has to deal with this race between feeding the host of the progeny, the parent of the progeny, and feeding the progeny. That's a real trade-off that happens for those, like in the case of sexual reproduction, the female has to deal with the fact that some of her energy is now going to the child. Her metabolism often adjusts pretty significantly as a result of that. So again, this is just a cartoon picture. The Rolang code that I have on my slide in front of me is very, very simple, but it does sort of capture something essential about these characteristics of life. And again, you can divide this into an independent analysis and decision-making mechanism versus an action that's taken with respect to that decision. which allows one to independently refine those two modules. That turns out to be something that happens quite often in lifelike settings, because these kinds of control structures in the biological world are complex and it's difficult to get right. And so wanting to preserve structure in a certain way while adapting structure gives rise to this kind of split. If you get an analysis and decision-making procedure nailed down, if you can reuse that across a wider range of cases just by changing the action part, that kind of reuse is favored by natural selection. And then it also turns out that, metabolically controlled continuation and autonomous reproduction are, again, just part of the story. Life has functional behavior. One of the ways that we think about this is the physicist doesn't really talk about the purpose of the orbit of a planet or the purpose of the gravitational effect of a star. But when you go up through the ranks to biology, biologists are all but forced to speak of the purpose of the immunological response to the viral infection. It's hard to avoid that kind of language when you're talking about lifelike phenomena. Mm-hmm. There's this question that arises that has to do with, can we modify our lifelike behavior to account for functional behavior? With the row calculus, it's actually pretty easy because we can make it parametric in functional behavior. So instead of P being parametric just in the channel for a food source, it's also parametric in some functional behavior. And let's say we supply it as a name. So it's parametric in S for the food source and at B, where B is some functional behavior like the web weaving behavior of a spider. That's an example of some functional behavior. In the case that it does have enough energy to continue, and the case where that energy is not being used for the reproductive process, then when it continues, it also engages that functional behavior. So the continuation is P in parallel with whatever that functional behavior might be. And the nice thing about this is, again, it's like the code that I'm looking at on my screen, it really hasn't changed very much. As I add these lifelike characteristics, the code itself is remaining relatively stable, which sort of gives us some degree of confidence that we might be in the right direction, moving in the right direction. Yeah. The other thing to point out is that if I go back to the original row calculus paper and I look at the way we've encoded replication in the row calculus, the interesting point is that the code that we've written down is not much more than elaboration of that code. In fact, in the paper, I point out that the encoding of pi calculus replication that I've given runs away. It's a runaway process. And that reflects the semantics that Robin gave for replication. It's like nobody ever liked Robin's semantics for replication, precisely because it was an infinitary object. And what you really wanted was some kind of guarded replication. And this is, and I point out that this could be done, but I don't supply the code. And you can see this as me finally saying, okay, well, if you haven't been able to write it down, here's a version of it.
Yeah, that's great.
And so it's interesting because it was always this lifelike harness was sort of always present in the row calculus. So what have we got in terms of our lifelike characteristics? Well, we've got metabolically controlled continuation, autonomous reproduction, and functional behavior. But life also adapts, at least on planet Earth. A good chunk of that generational adaptation is genetically controlled evolution. The interesting thing about the row calculus is that it gives us the reflective part of it. When you have a process, say, P of S and at B, like we've been talking about, if you took the code of that process, that gives you something that is akin to the genome of that process. So if we think of the process itself as the phenome or the creature, then the genome is represented by the code of that process. If we modified the code of that process, we would get a different phenome. We get a different creature.
That's such a cool idea.
It's a lot of fun, and we can go pretty deep in this. But before I go down that path, I just want to point out that now this does in fact relate to Casper-like validation. In particular, we can now implement the notion of slashing as a form of starvation. So if we have a validator behavior, if we starve that validator of food, then that corresponds to slashing it. One of the things that's been very tricky with respect to proof of stake in general has been how to represent the fact that validators are absolutely going to want to de-risk their investment. And so it's hard to force them into a situation where one staking address equals one instance of the validator behavior. Mm-hmm. And if that's not the case, then you run the risk of not having a secure network because you don't know how much compute is really associated with the staking address. But here we can be quite explicit about the size of the population associated with a staking address. And that staking address is kind of explicitly represented by the S, the food source address, that is the parameter of this lifelike process. But the detail, it gets even more fine-grained in terms of how this analogy maps onto the way we think about Casper and RChain. So in particular, we can think of the food is the token. And the energy that the food is converted to is gas. So the internal metabolic transformation and the internal metabolic regulation of the continuation of the validator behavior is done in terms of gas, which is our notion of energy. The food is the rev or whatever staking token is being supplied in order to run the validator. But the analogy goes even further because, as I've tried to suggest, staking corresponds to if you starve the process of food, then it will go through apoptosis. It will eventually shut down. It won't be able to reproduce, and it won't be able to engage in any functional behavior. And the nice thing is you can do what we sometimes have called slashing to the bone, where you cut the stake all the way down and the validator can't do anything more. Or in this case, you can starve it so that only some of its population dies off. You don't have to slash all the way to the bone. You can have consequences of behavior. For example, if a validator equivocates, you don't want that behavior to persist at all. So you want to wipe it out. So the validator is lying, saying one thing to one side of the network and another thing to the other side of the network so that double spend could happen. You want to wipe out that population of behaviors. Yeah. But if the validator stumbled and there was some corruption in a block, so it either created or promoted an invalid block, that may not actually be the fault of the validator, right? There may be some extenuating circumstances. And so you could imagine punishing it for not having caught that problem, but not punishing it to the point where, it's just removed from the pool. And then, again, life is a wonderful analogy. The other side of this that's really interesting is that the functional behavior is now serving client requests. When we run this extra B thing, that's a contract that the validator has decided is worth running. The mapping of the lifelike behavior, which we did entirely from first principles in terms of how to model life, has now given rise to a harness that captures all of the salient features of the validators down to some pretty fine level of detail. So let me just stop there and just check in. Christian, does what I say make sense?
Yeah, it's making a lot of sense. One thing I was wondering is on this current slide, when you're splitting off a behavior from metabolizing some food, it seems you would also need to attach some resource dependence onto that behavior, or it would somehow need to remain tied to the organism. Otherwise, the organism could end up splitting off tons of behaviors and be doing multiple things at once.
Yeah, I'm so glad you mentioned that because I addressed that in the subsequent slides, and it gives rise to some really interesting analysis. So the perfect segue. In order to sort of increase the narrative tension, let me defer my answer for a bit and return back to this idea of using reflection to develop a notion of genetically controlled evolution of the validator behavior. And then I'll come back to what you're talking about. The two ideas fit together in an interesting way. So one of the things that we mentioned earlier was just that reflection gives us a handle on a way to represent the distinction between the genome and the phenome. The genome is the code of P and the phenome is P. For those people who are not as familiar or maybe haven't heard of it, there's a line of computer science research called genetic algorithms, and this was founded by John Holland. He has a seminal book called Adaptation in Natural and Artificial Systems. And one of the things that he does is he characterizes evolution as a kind of search. So he says that it's a feature search, and then he analyzes different approaches to search. So in particular, you could look at mutation as a way to search the feature space under selective pressure. And he compares that to what happens with sexual reproduction, and he identifies a genetic operator called crossover, where you have two organisms, each of which have a pair of genetic information. And so let's say we have a mother and a father. The mother has two parts to its genetic information, and the father has two parts to its genetic information. When they reproduce, the progeny can take part of its genome from the mother and part of it from the father. And this makes sure that there's an exploration of the features of the mother and the features of the father. Holland analyzes this and shows rigorously that feature search that is predominantly based on crossover with a tiny little bit of entropy from mutation is far superior to mutation by itself. Mutation by itself is largely a random walk and generally ends in bad results in a feature search that's subject to pressure.
But somehow crossover has a way of strengthening itself or guiding itself.
That's exactly right. There's a little bit of subtlety. The genetic information ultimately needs to be able to expand. We're talking about crossover plus mutation, and the mutation every once in a while has to expand the features available. There's some subtlety there that I'm not going to go too much into the details about that, but I heartily recommend that people go look at the area of genetic algorithms and how they apply to what's called genetic programming. So using genetic algorithms to have computer programs generate computer programs. And I heartily recommend Holland's original book, Adaptation in Natural and Artificial Systems. But I just want to point out that using reflection, we can define crossover for row calculus processes in general, which means we can define it for the functional behavior. Just as an example, if I have a functional behavior that is a par, so if I have B that is equal to a B sub M for either male or mother, depending on which way you want to take this, in par with B sub F, which is either female or father. So I'm being completely agnostic as to the order in which these are placed. And then you have a B prime, which is equal to, B sub M prime in parallel with a B sub F prime. We now have that bipartite structure that was necessary for the crossover operator. And so I can define a collection of progeny where you take the components from the mother and the father. So this is just, combinatorics, right? So you can get a B sub M in parallel with a B sub F prime, or a B sub M prime in parallel with a B sub F, or you can get the B sub M in parallel with the B sub M prime, or the B sub F in parallel with the B sub F prime. So those are the four possible progeny. And you can do a similar thing for four comprehensions, right? If you pair up four comprehensions, you can define a crossover operator. And in fact, for all of the two-part term constructors, you can define these genetic operators.
The one
Go ahead.
for the for comprehension is really interesting because not only are you mixing the continuations, but where you're looking, and then vice versa, you can evaluate.
No, I agree with you. I think you're spot on because you get more progeny because you have this ability to turn code into running processes and running process into codes. You have more total options for generating progeny. That's an important observation, I think. Now, you made a really good observation when we talked about this a while back. You said that if you recursed these operators, that might be a way to generate new alleles.
Yeah, you could completely interlace two codes, and that would produce a ridiculous amount of possible progeny, and then somehow you want a good way of selecting from that randomly or something.
That's correct. Like so you could imagine applying this to the generation of tests. I have often used in testing a technique called fuzzing. In fact, I've got a whole approach to this where I define a mechanism whereby you generate a stream of terms. So you give not just one, but an infinite stream of terms. That stream is seeded by some initial set of conditions. So here we're talking about generating that stream of terms from this genetic like reproduction. But we now, in the case of testing, we have a clear sense of what it means for a test to succeed. It means that when you put it in parallel with some program that you're testing, it causes that program to fail in some way or to behave in a manner that doesn't comply with its specification. And so you can now run this whole mechanism, and whenever a test is successful, then it's selected as more likely to reproduce. If you put all the pieces together, you get this infinite stream of tests that are getting better and better at breaking your programs, which is kind of cool.
Yeah.
So now we can tie it back to the question that you raised earlier, which is how do we control the functional behavior part, right? So if the functional behavior part is a smart contract that has been deployed by a client, how do we resource constrain that? And it's related because if you analyze how reflection is showing up in the row calculus, it shows up as a loop in the syntactic constructors. So you get a kind of fixed point. We talked a little bit about that. Mike sort of pointed out this construction when we talked about the row combinator stuff last week. You can do that loop here. At a minimum, you could pick out a B that is also metabolically controlled. You could have a B that is an iteration of the validator harness, this lifelike validator harness, on top of some other more constrained functional behavior. That's how we answer your question, right? I can just articulate B so that it's only allowed to run in this metabolically controlled approach. The next piece of the puzzle that's really interesting is that we can make this a fixed point. You know, we started with the idea that B is equal to the lifelike process applied to S and some B prime, where B prime is the actual client request. Now we can modify that and say that this recursive operator, say R of P, is defined to be P of S of R of P. So now we've got the loop, and this gives you this infinite tower of validator behaviors. I actually talked about this with Jack Eck, who worked with me on the DAObug paper and did some initial work on Rolang, that you could have this infinite tower of validator behaviors. And here now we've sort of written that down. We've bitten the bullet and said, well, what's a validator-like behavior look like? Okay, here's what it looks like. And then it turns out that it's written in such a way that you can characterize this tower as a fixed point of this recursively closing up the equation.
What does this tower mean exactly?
What it means is that you've got a wider notion of validation, right? So it's like a tower of simulators. Each behavior is being simulated at the level outside of it, and so it's very, very reminiscent of the reflective tower of 3-Lisp. So for people who are interested, Brian Cantwell Smith came up with the idea of reflection initially and coded it up. He was a student at MIT, coded it up as 3-Lisp, but he expressed it in terms of this infinite tower. And it was quite mysterious to a lot of computer scientists until Friedman and Wan published a seminal paper called The Mystery of the Tower Revealed, in which they give a non-reflective account of the tower, which is kind of similar to this fixed point construction that I've given here.
They don't tell you about this kind of computer science and
it's good, fun stuff. I heartily recommend that people read Brian Smith's PhD thesis and then The Mystery of the Tower Revealed. Brian built a language called 3-Lisp, and then Freeman and Wan came up with a language called Brown that is gives you the same kinds of behaviors, but with this non-mysterious presentation. Interestingly, also, we can classify different lifelike behaviors. The two ideas, the sort of genetic programming idea or the application of genetic algorithms and classification actually go hand in hand. Just recognizing that a lot of biology is, essentially categorizing things, classification schemes, right? So kingdom, phylum, class, order, family, genus, species. That's a template or a rubric for the biologist to sort of give some structure to the zoo of life forms. But the ladle approach, the generation of types, allows us to come up with some types that cover, at a minimum, the functional behaviors. So you could imagine using this both at compile time to insist that the only functional behaviors that get attention fit compile time characterization, of a certain behavior. But you could also do it at runtime, right? So you search for behaviors that match a particular type across a stream of submitted client requests. So this allows the validator to be selective in terms of the functional behaviors, the client request that it's accepting. I think that's of considerable value, right? Because it allows for the evolution of a market, right? Where validators are favoring certain kinds of client requests on the basis of what it is that they do.
That's hugely important.
Yeah, that's an advantage that is not currently contemplated in other smart contracting platforms.
In other platforms, they just have no way of distinguishing, and they're just validating requests.
They're just validating, yeah. Like in Ethereum, the validators don't have any view or insight into the client requests themselves.
Wow.
Yeah, this is a fundamentally different approach. But also, it's different because we can lift our genetic programming techniques at the term level to the type level. All those crossover operators that we defined for terms, we can also define for types. And this is because what we sort of discussed earlier was that every term constructor that was bipartite, right? It took, either two processes or two names or a name and a process. Those all can give rise to obvious crossover operators. With Ladle, every term constructor is also a type constructor. That's kind of one of the main points. And so we can lift all of our crossover machinery up to the type level. And this is important because we can now do this co-evolutionary thing where we're looking to classify things at the same time that we're looking for things. An example for me, just from my own experience, is the mathematical process, right? So my inner dialogue is something like, this must be true, right? And then another part of my brain says, wait a minute, what about this counterexample, right? And then, the other side goes, the player is proposing theorems, so these are types, and then the opponent is proposing counterexamples, and those are terms. There's a kind of type-term dialogue that's happening, which is co-selecting for classification schemes and counterexamples to those classification schemes. This is the kind of thing that we can now do. We can automate with the row-lang machinery, with the row calculus machinery. And I think that that's incredibly powerful, both on the scientific side, to go and do search for lifelike computational behavior and classify it, but also it's incredibly powerful on the blockchain side itself.
You could probably utilize huge results in game semantics to make this search really nice.
Oh, I agree 100%. One of the things that I have talked a lot about in private, but not so much in public, is my opinions about deep learning and its approach to AI. When I was growing up in computer science, AI was not just neural networks. It was a much bigger field, including genetic algorithms. I've become rather sad that deep learning has dominated the scene recently because it suffers. It's not compositional. It's like if you have a neural net that recognizes the age of faces and a neural net that recognizes the expression of faces, it's not so easy to combine them into a neural net that recognizes the age and expression of faces. Mm-hmm. Now we can contemplate some different architectures there, but the point of things like the row calculus or the lambda calculus or some of the various computer science machinery that we've applied in the R-chain setting is that it's compositional from the ground up. So you have compositionality built in. You don't have to go and discover compositionality later. And that turns out to be fundamental to composition itself. Compositionally defined structures typically coincide with monads or, at the very least, some kind of endofunctor. So trying to find it post facto is often misguided, to put it bluntly. So here we've got this compositional setting, and then the other side of this is, I do understand. Mike has told me that there are some techniques for trying to find the why of a neural network, but here we have the building block. We can actually say what the notion of an explanation is, right? So a run of this classification counterexample kind of thing gives rise to a crisp notion of explanation. And we've organized it so that we can get a why, and we can compose. And we've done this all in sort of an extremely compact form in a setting where we can resource constrain these genetic algorithms. So we can resource constrain these search techniques. And I think that makes for probably some of the most powerful AI building blocks that you could have. So that's why I think this ends up being kind of fun in that regard. But there's a wider picture that I want to get to next time. Just as a teaser, we can take these ideas about lifelike infinite towers of simulations and reapply them to our notion of an emergent space-time and start to get a really different angle on how to think about physical phenomena.
Amazing stuff.
Well, we're having fun, right? I mean, the whole point of research is to have at least have some fun. Yeah. Probably most of the ideas are wrong, but maybe once in a while there's some gems in there, but we've got to have some fun along the way. And any final thoughts or comments on your side, Christian?
I just really appreciate that this is your guiding perspective. I think it is so important. It's not a coincidence that it's going to be a natural and better framework, and I think it's going to make programmers think differently about how they're designing all this stuff when there's this clear analogy and the programs are not just floating by themselves, but they're explicitly like these organisms that are subjective and constrained. And I just think you showed a ton of really great ideas today, and I think they're all awesome.
Well, that's very kind of you. Very kind. Well, let's, hopefully we'll get more and more people pounding on them, and we'll see if they have any merit at all.